Okay, so we've got section 14.5 here in the game theory chapter, which is Introduction to N-Person Game Theory. So we are talking about basically any game now where rather than having two players, there are going to be three or more players. So if you think about this, this is like any game like Scrabble you could be playing where there's, three people, four people. It could be multiple businesses in a specific industry all competing for superiority in just any game in general with three or more players. So here, like we said, we're going to have a set N. Go blue actually for this. Set N is going to be any set of players greater than two here. And that's going to give us an N-person game. So with these N-person games, we're going to be specifying a characteristic function, which is going to help us define the reward for the specific game here. So what we have is for each subset S of n, the characteristic function v of a game is going to give the amount v of s that the members of S can be sure of receiving if they form a coalition and work together. So S here is going to be any combination of players out of our total set n that are playing the game. And v of S is going to be the guaranteed reward. Do that. The guaranteed reward from teaming. So in a game where there's like three players, if player one and player two work together, then the characteristic function v of 1 and 2 is going to be the reward that players 1 and 2 will earn after they decide they're going to work together. So here we have our first example. Joe Willie invented a new drug. Joe cannot manufacture the drug himself, but he can sell the drug's formula to company 2 or company 3. The lucky company will split a $1 million profit with Joe Willie. Find the characteristic function for this game. So I think a good first step is to define who is what player here. So let's start off and say Joe is going to be player 1 for us. Company 2 can be player 2. And then company 3 is going to be player 3. And it's fair to start off by saying that Joe needs at least one company or else, obviously, Joe can't manufacture the drug himself, which is what it says up here in the problem. So we know that the characteristic function of the empty set, which would just be obviously a team with nobody on it, is going to have a reward of 0, is going to equal the reward from having just player 1, which is just Joe, which is also going to equal the reward for just player 2, because just the company 2 can't do anything without the formula. Same thing goes with company 3. They can't do anything by themselves. And lastly, if companies 2 and 3 team up without Joe, they don't have that formula. So again, their reward is going to be 0. So all of these are going to equal $0. This is the first part of our characteristic function here. And I'll switch colors. Now, there is a potential for a coalition to earn that $1 million profit we talked about. So this is going to be Joe with at least one company. And here we're looking at the set V of 1 and 2, which could be Joe working with company 2. It's going to be the same reward as Joe working with company 3. This is also going to be the same total reward as Joe working with companies 2 and 3. And all of this is going to be that $1 million reward. And again, even though we have a different number of players in, say, this set and this set here, the net reward for this coalition of just Joe and company 3 and then Joe with companies 2 and 3 is still going to be that $1 million. They're all going to be split in that million. So they are actually equal with regard to their characteristic function. So this is our solution for the first example. Moving on, now we have another definition, which is the superadditivity definition. So you basically take any two subsets, A and B, where there are no players in common in these two subsets. Then if we take the union of the characteristic function, so if you take the union of A and B and find the characteristic function of it, it's going to have to be greater than or equal to the sum of the characteristic function of A and the characteristic function of B. So what this is saying here is basically the union of A and B is at worst the sum of A and B alone. Which if you think about this, this makes sense because if the union was anything less than A and B, obviously A and B wouldn't synergize in the first place, so this would never happen. So the union has to be realistically better than having these two groups apart, otherwise they would never combine. So this is superadditivity. So again, this description down here kind of covers what I just said, where the union has to be better than or the same as the two groups on their own. And we also have the reward vector definition. So what this is basically is if you have a bunch of players on one solution here, call it x, then we can make a vector with x1, x2 up to xn, where each player has a specific reward specified in this vector. So this is just all fancy for saying the reward vector is a vector containing each player's reward for a given solution. So this takes us into our next example here. Each of 4 property owners has 1 bag of garbage and must dump it on someone's property. If B bags of garbage are dumped on the coalition of property owners, then the coalition receives a reward of negative B. So find the characteristic function for this game. So again, I'm going to start off by defining our players. We have 4 owners. So we're just going to say we have player 1, player 2, player 3, and player 4. And start off by just stating some facts with the situation of our game here. Ideally, the coalition will dump their garbage on a property outside of their coalition. So I'm just going to say they will dump on the others because you're not going to want to hurt the overall reward for your team because that'll hurt your direct reward. And secondly, another thing that we can notice off the bat is if everyone joins the coalition, everyone teams up, we'll have V of 1, 2, 3, and 4. And no matter what, our total score is going to be -4 here. Because regardless of who they're dumping the garbage on, the coalition's total reward is going to be -4 because we have 4 bags of garbage dumped on someone's yard. So, moving forward from here, if we have any group of 3 teams, we'll say, so I'm just going to call this V of 3, what we're going to have is -1. Because if we think about this, there's going to be that one guy that's left outside of the coalition, and he's going to throw his garbage on someone's yard that isn't his. So let's say you have, this could be the same thing as players 1, 2, and 3 working together. So now if you draw a picture here, you've got 1, 2, 3, and 4. Let's say so we said 1, 2, and 3 are working together. So player 1 is going to throw his garbage on player 4. Player 2 is going to throw his garbage on player 4. Player 3 is going to throw his garbage on player 4. And it doesn't matter where player 4 goes. He could go here, here, or here. And ultimately, this team is going to have -1 as their final score here, if that makes sense. So then the next logical step would be to say if we have a team of 2, then we're going to have, at worst, a score of -2. So that would be like if we had player 1 and 2 up here working together. At worst, 3 and 4 are both going to dump on these guys. There's a chance that 3 could throw his on 4 if they're not teamed up or anything, or 4 could throw it on 3 and they could have a score of -1 or even 0 if these guys throw on top of each other. But at worst, which is what we have to account for because we're looking for the minimum possible reward they could get, a team of 2 is going to have a score of -2. So finally, if we have a team of 1, at worst, if everyone throws their garbage on this one guy, he's going to have a score of -3. So, looking at these 3 numbers here, let me change my color. A team of 3, a team of 2, and a team of 1. What we have is V of a set of size S here is going to give us a reward of -4 minus the cardinality of that set. So however many members are in that set is what's going to be that cardinality of S here. So for example, if we have the first one here, V of 3, we're going to have -4 minus 3, or just -1. And that goes on for V of 2 and V of 1 here. So I'm just going to rewrite our solution kind of clean down below. We have, do it as a piecewise, V of S is going to equal -4 minus the cardinality of S. For cardinality is less than 4. And then if we have V of 1, 2, 3, and 4, we're just going to have a guaranteed score of -4. And this will be if the cardinality of S is equal to 4, obviously. So that is going to be our final solution here. And we will move on to problem 1. So again, you guys should be trying these on your own if you want to. And then I'll just be something to look back on afterwards. Player 1 owns a piece of land and values the land at $10,000. Player 2 is a subdivider who can develop this land and increase its worth to $20,000. Player 3 is a subdivider who can develop the land and increase its worth to $30,000. There are no other prospective buyers. Find the characteristic function here for the game. So for basically, we'll just kind of break this down into pieces here. Obviously, player 1, player 2, and player 3 are already defined. So player 1 owns the land, it tells us in the first sentence here. So that being said, any coalition without player 1 is going to be equal to 0 because they don't even have that land to increase the worth for. So we have V of empty set equals V of player 2 equals V of player 3 equals V of players 2 and 3, which all is just going to be equal to $0. Now, if we have just the land, this would just be player 1 without any help from players 2 and 3. We're just going to have V of player 1, which is that initial value of the land, or 10,000. Now, if you look, we kind of have a mini upgrade that's being offered from player 2 of 20,000, and there's kind of a big upgrade here from player 3 for 30,000. Just how I'm going to describe it. So if we do the mini upgrade, this is going to be characterized as V of player 1 and player 2, and that's going to give us a reward of $20,000. And then lastly, we have the big upgrade, which is going to be V of player 1 and player 3. Or it could also be, even though player 2 is not doing anything here because the big upgrade comes from player 3, if they all work together, they're going to again have that reward of 30,000. So all of these blue lines here are all a part of your solution here, and that's the end of the problem. And that will conclude section 14.5. Thanks.